when we started this chapter, we introduced the kinetic molecular theory. It's a theory that says that you can explain the behavior of gases, the properties of gases, things like gas pressure. And you can also explain the gas laws in terms of motions of the molecules. We assume that a gas consists of a lot of very tiny particles that are in constant random motion. So here's a container, and here are a bunch of gas molecules. There's a lot of space between them, and they are flying around at pretty high speeds. So that's the first assumption that we have. Now, we're going to assume that the molecules are moving, that the molecules are tiny compared to the space between them. And this is not a bad assumption. I mean, in air, the distance between molecules is about 1,000 times their diameter. So air is mostly empty space at room temperature and room pressure. So we can essentially treat molecules as mathematical points. They're just a point with no volume. And we can derive the gas laws from that assumption, and we get a very simple form for the gas law. That's where we get the PV equals nRT. It assumes these two things. We also assume that the molecules don't attract or repel, but they don't interact unless they are actually head-on colliding. So they don't interact in any way. This means that they're going to move in straight lines, even when they pass very close to each other. The only thing that is going to disturb them when they're moving is a collision. So here's a gas molecule moving along a line. If it hits another gas molecule, it's probably going to ricochet off of it. And this gas molecule might have been moving, so it ricochets in another direction. This collision is called an elastic collision. In that the total kinetic energy is the same before and after the collision. So in everyday life, an elastic collision would be like something you would see between pool balls on a pool table. Here comes the cue ball in and it hits another ball, and pretty much their kinetic energies the instant before and the instant after the collision are the same, the total kinetic energies. As the balls roll along the table, they'll lose a little bit of their kinetic energy due to friction. And sometimes you will get inelastic collisions. What if you tried to play a game of pool with some rubber balls? Well, when rubber balls hit each other, they'll hit and they'll deform a little bit. And you won't get quite an elastic collision. And it will be very hard for you as a pool player to predict the angles, what's going to happen when you hit the cue ball on another ball. If it's an elastic collision, it's a lot easier to see what's going on. It's a lot more predictable, and you're not losing energy. Alright, so this is actually an assumption that goes into deriving results in the kinetic molecular theory. One of the equations you can derive with kinetic molecular theory is PV equals nRT, which is the big ideal gas law equation in this chapter. It is the big central relationship that we've been talking about up until now. Now, it can also derive how the speed of the molecules changes with temperature. Really, the molecules are moving at all different speeds. If you look at the fraction of molecules versus the speed, you get kind of a curve that looks like this. This is an exponential curve. And you see that some of the molecules, a big fraction of the molecules, have this speed here. This is the most likely speed that you can have. And it happens to be the most probable speed happens to be square root of 2 RT over m, where m is the molar mass. We have been using that as a symbol for molar mass before. If you look at average speed, it's off a little bit from where the peak is in the distribution here. So the average speed, it might be like, it's very close to that, but the average speed, where I'm drawing this line down so it cuts the area under the curve in half, the average speed is going to be about 8 over pi RT over m. And there's another average that people look at, and it's called the root mean square speed. So you took all the molecular speeds and you squared them, and you added them all up and averaged them. And then you took the square root of that. That would be called the root mean square speed. And that's equal to you might be wondering, do I have to remember all these equations? And do I have to know how to define an RMS speed and an average speed and a most likely speed? It'd be nice if you did, but you don't really need to. What I want to point out here is that as the temperature goes up, as you make the T bigger, all of these speeds get bigger. So higher temperature, faster average speeds. That's one thing I want you to see from these equations here. And what about the molar mass? How does that affect the average speed of the molecules? If you leave the temperature the same and you make the molar mass bigger, it's on the bottom here, it's going to make the average speed go down. So if you have a higher molar mass, slower average speeds. This is what I do want you to know about how average speeds are related to temperature and molar mass. I won't ask you to do a calculation with this. Look at this distribution again before we leave it. This is at one temperature. So this might be at, say, room temperature. What happens when you heat the molecules up? You'd expect with a higher temperature that you get faster speeds, and you will. But what you have here is the area under the curve is the number of molecules that you've got. Alright? So that area has to stay the same. So we're going to shift it at a higher temperature. It's going to shift. It'll get lower and broader. And that would be at a higher temperature. So you will see that your distribution shifts to a faster speed at a higher temperature, but it also gets lower and broader. Now you might be recognizing these curves. in the current time, our lives are kind of being upset by exponential curves like this. If you look at the fraction of people you have versus time, fraction of people who are sick in an epidemic over time, you get an exponential curve that mathematically is very similar to the one we were just looking at. It's very similar to that. And if you do something to shift the peak further, like social isolation, this is the flattening the curve business that everybody is talking about now. The area under the curve has to stay the same. So in other words, the same number of people are going to get sick when you flatten the curve. They're just not all going to have a higher, there's not going to be that high a peak of cases at one given time. So if this is your hospital capacity here, you're only slightly exceeding hospital capacity with this flattened curve, whereas you're greatly exceeding it if you do nothing. The math is the same. This is one of the reasons why people study these kind of things. This distribution here appears in some surprising places in science. All right, so there's some phenomena that we can explain with this. For example, we can explain the speed of sound in different gases. The higher the average speed of the molecules, the faster the speed of sound. Sound can carry faster in a gas that has faster moving molecules. So let's look at helium versus, say, oxygen. Now helium has got a molar mass of about 4 grams per mole, and oxygen has a molar mass of about 32 grams per mole. If you look at our equations for average speeds, the one with the bigger molar mass is going to have the lower average speed if they're both at the same temperature. Higher M, slower speeds. So this will have a slower speed of sound. Sound will move more slowly through O2. And this will have a higher speed of sound. So, you know, when you breathe in helium, you get that high-pitched, squeaky kind of sound. The pitch of your voice changes. This is why. It changes because of this effect that we're talking about here. What else can you explain? Suppose I've got a little pinhole here, and I've got gas coming out. This situation where you've got a gas in here escaping through a little pinhole is called effusion. If my gas was a mixture of helium and oxygen, what would effuse faster? Okay, well, it'll depend on the speed of the molecules. The effusion rate, let's see, higher average speed for the molecules is going to give you a faster effusion rate. Now, since the helium is going to have a higher average speed, the helium will effuse faster than the oxygen. The oxygen will seep out of this pinhole slower, and the helium will seep out faster. all you got to do is look at the molar mass. If both of these gases are at the same temperature, the one with the lower molar gas will have a higher average speed and a faster effusion rate. Who cares? Well, this again is something that changed the world. This gives you a way to separate two gases. And it was used to separate isotopes during the Manhattan Project in World War II. We were able to figure out a way to enrich uranium using effusion stages faster than the Nazis were, and we developed the bomb before they did. Or else we'd have a man in the high castle type scenario. Another effect that you get is diffusion. So suppose you've got some helium here in a tube, and you've got some oxygen here, and you've got a wall between them, and you take the wall away. What will happen is the helium molecules will move into this space, and the oxygen molecules will move into that space. And which happens faster? Well, the higher average speed means faster diffusion. So effusion is when you're spraying the gas out of a pinhole. Diffusion is when it's moving into an area where it wasn't allowed to be before. So you'll see the helium diffuse over here faster than the oxygen will diffuse over there. So these are some of the things that you can explain with the kinetic molecular theory.